another exam walkthrough for you. This one's from 2024 October, Unit 2. And we've got 2024 Jan, Unit 2. So we're going to be doing these two questions. There's going to be question number 17. So you can pause the video and solve it yourself. And this is the question number 13. And after that, I'll show you the mark scheme and the examiner report at the end for both the questions. So the first part of this question is that the refractive index of water is 1.33. Calculate the speed of light in water. Okay. So here's the formula. N is equals to C over V. Now many students, when they solve these type of questions, they wonder where did this formula come from. So remember, there are two key formulas to Snell's law. The first is this one, which I'm sure you're familiar with and you know how to use as well. And the second one is going to be N1V1 is equals to N2V2. It works the same way. We go from one medium to the other, right? So how I write, it goes from air to glass. So these are going to be the values for the air, refractive index of air, and the angle in the air medium. And then this is going to be for the glass. So this is going to be the same way this works as well, right? But how do we get from this formula to this formula, right? That's what you might wonder, right? So let's say that we're going from air and we're going into water, right? So we're going into water. Now in air, the refractive index N1 is just 1, so we cancel this out. And V1, which is the speed of light in air, is approximately equals to C, which is the speed of light. So we just write C here, and then we write N, which is the refractive index of water, and the velocity of light in water, and then we get the formula N is equals to C over V. So this is going to be the speed of light in water and the refractive index of water. And then you can, I think, solve it quite easily. You just have to do 3 times 10 to the power of 8 divided by 1.33. And you get the answer as 2.25 times 10 to the power of 7 meter per second. We'll be looking at the 6th marker, which is a person is swimming underwater in a lake. The person looks up towards the surface. 3 rays of light A, B, and C are incident on the surface of the water as shown. Each ray changes direction at the surface of the water. Light from rays A and B reaches the person's eyes. Most of light from rays C and C does not reach the person's eye. Okay. Explain the path of rays A, B, and C. After each rays changes direction at the surface of water. So we know that A is going to reach the person's eye. Now what's going to happen to A, the ray A right over here. Now let me draw the normal first. So this is the normal line. Okay. So what's going to happen is that ray A will refract. So it will refract because it's going to go from air to water. So we can see that air is optically less dense than water, or you can say the refractive index of air is less than the refractive index of water, or you can say that the speed of light in air is more than in water. Okay, so saying any of this one thing will get you 1 mark, and the next mark will be that your ray A will refract, and it will bend, or it will actually refract. Don't use the word bend, use the word refract. It will refract towards the normal. Okay, so first mark you get for writing any of these things, okay, one of these. Next mark you get that A is going to refract, and it's going to refract towards the normal when it enters water, and so it reaches the person's eye. Okay, so that's going to give you the second mark. So these are 2 marks right over here. The next mark you get, 2 marks you get, is talking about the ray B. So ray B, the way it can reach the person is that if it totally internally reflects. So if it reflects and it doesn't refract. So in this case, what should happen is that we have total internal reflection. But before you even talk about total internal reflection, write about the fact that the angle of incidence is greater than the critical angle. And we're going from more dense to a less dense medium. So more dense to less dense medium. So total internal reflection will occur and it will reach the person's eyes. Okay, so light will totally internally reflect. Okay. And then we're going to talk about C now. Okay, so this is going to give you 2 marks here. Okay, talking about these 2 things and talking about the fact that ray B will totally internally reflect. And then 1 mark again for any of these points, and then 1 mark for talking about light refracting towards the normal. Now I just want to point one thing out. When you talk about refraction, don't talk about bending of light. Talk about the refraction. Okay, specifically, they want to see that word. Okay, that's why I said don't say when you have the question above that this ray will bend towards normal. It's better and much more accurate to use the word it refracts towards the normal. Okay, so try to stick with the word refracts. Okay, so here's the answer. It's just what I've explained. Okay, so it's in my own words, but it has the key points. So yeah, and I think that's all for this question. I'll show you the full mark scheme and examiner report, and then we'll move on to one more question. Moving on to 2024 Jan Unit 2. It's going to be the final question of this video. So you can, I hope you've tried the question out, and yeah, let's just get to solving. So a glass is filled with transparent hydro beads. The glass is then filled with water. The beads under the surface of water seem to disappear as shown. The refractive index of hydro beads is very similar to the refractive index of water. Explain why the hydro beads are difficult to see when they are surrounded by water. So to help you understand further, let's go through this example. So first let me label everything here. This is water. This is gonna be your ray of light. This is gonna be the hydro bead. For simplicity, I've drawn it as a square shape, so hydro bead. And then above this we have, let's say this is example number 1, this is example number 2. In the example number 2, there's no water, so this is just air. And this is again the hydro bead. Okay, so hope this is clear. I'm going to erase this. Now, I'm not focusing on what happens to light when it enters and when it leaves. We're just focused on what happens inside. Okay, now let's look at this. So we're gonna have the light coming in. This is air. This is air right over here. Then we're gonna enter the hydro bead, which is more dense. Light will refract, and then again we'll enter air, and light will refract away from the normal. The reason this happens? Well, that's because the speed of light in air is more than the speed of light in the hydro bead. It's because the hydro bead is optically more dense than air. So because of that, we have the refraction occurring over here. Now, let's look at the example below. Okay, now let me clarify one thing about this as well. Because of this refraction happening, and this refraction occurs, and that's the reason why your hydro beads can be seen. But then the question remains, why can't we see the hydro beads over here? Well, that's because, notice, we have the light entering, the light ray entering. It refracts a little bit, okay? And then it refracts a little bit here as well. Very little. It's almost like the ray is the same. Okay, now let me just show for comparison. Let's say this ray continued in its path. It would go like this. Now let's say this ray continued its path, it would go like this. Notice the difference? This ray, okay, if it continued moving straight, but due to refraction, notice the path changed. Here, notice the ray should have gone like this, and the path changed, but not too much. Here you can notice the path changed by a lot because of refraction. Here, the ray refracted very little. There was very little refraction because the refractive index of hydro beads and water is almost the same. So speed of light in water and hydro bead almost the same. Okay, it's almost the same. Because of that, very little refraction occurs. And that's why we see both water and the hydro beads not as distinct from each other. They appear to be the same. So hydro beads, they don't have any distinction here. They just appear to be like they're in the water and they have dissolved in the water, even though they're present there, because of the refractive index being very similar to the refractive index of water, and that's the clue they have given you in the question. So this is the answer. Little refraction as speed of light in water and hydro beads is almost the same. So no change in speed of light as the medium change. Okay, that's going to give you 1 mark here, and the second mark is this point. Okay. Now let's move on to the next part, which is just calculation. Next 2 parts are calculation parts. So we have I and II, and let's just do this. This doesn't appear to be that hard. A ray of light is in air is incident on a damaged hydro bead. The diagram shows the ray until it is incident on the damaged surface at position X. Okay. The refractive index of the material of the hydro bead is 1.38. Calculate the angle of refraction. We can just use Snell's law. So we can use Snell's law, and then we're going from air to hydro bead. So this is going to be the values for the theta in air and the refractive index of air, and this is going to be for the hydro bead. So I've plugged in the values, and now I'll just solve it. And you should get the angle of refraction as 29 degrees. The last part of the question says, complete the diagram to show what happens to the ray at position X. So what would happen to the ray at position X? Now, a couple of things could happen. It could refract, and it could refract away from the normal. It could totally internally reflect. So those are 2 things that could happen. So let's just see what would happen. I think this is talking about total internal reflection, particularly. So let's find the angle of the critical angle. Okay, and then compare it with the incident angle. So that's going to help us out. So let's do N1 sine theta. So let me just write this down first. Sine theta 1 is equals to N2 sine theta 2. So here we're going from the hydro bead to air. So I'm going to go from hydro bead to the air. Okay. So at the critical angle, your incident ray here should be perpendicular to the normal. So should have a 90-degree angle right over here. Okay, so we're going to have N1, which is going to be 1.38, sine theta 1, which is going to be basically the critical angle, is equals to N2, which is 1, and then sine 90. Okay. Remember, I think I've said a couple of times the conditions for total internal reflection. You go from more dense to less dense medium, and then your angle of incidence has to be greater than the critical angle. So we just want to fulfill those 2 conditions. So first condition is fulfilled. We're going from more dense to less dense, and now we just have to verify if the angle is greater than the critical angle. So here we have this, and I'm just going to find the critical angle, which is going to be 46.4 degrees, and that's obviously less than 50 degrees. So angle of incidence is greater than critical angle. So light will totally internally reflect. Let's just draw this. Total internal reflection. Okay. So that I think does the question, and you can just look through this, and I'll show you the mark scheme and examiner report.